Shall we start? Okay, so hello everyone and welcome to this session of a mathematics seminar. And today we have a pleasure to hear Jeanne Scott, who will talk about closed symmetric functions.
Thank you. And, thank you, Jeremy and Vincent, for the opportunity to give a talk. So I'm told I'm inaugurating this tablet, so we'll see how it goes. If the font is too small, I can zoom, so just let me know. And I think that Francois already pointed out there's a typo, so I don't know, how do I write here?
Before the T.
Let's see if I can move it. Get a way to, I can erase it next time. So this, I'd like to talk about a project I've been working on for a few years now, or aspects of a project, which involves a close cousin of the Young lattice called the Young Fibonacci lattice. And like the Young lattice, it supports a family of functions whose multiplicative structure somehow recapitulates the poset or lattice structure, and also carries with it a representation theory. So, and some nice combinatorics. So, I think what I'll do is to begin, I'll review some things about the partitions and Schur functions, just so that we're on the same page, and with the aim of kind of trying to distill those features that I want to replicate in this clone theory. So, see how this goes. So yeah, so partitions. So that these will just be monotonic, weakly decreasing non-negative integer sequences, and how do I? If I want to point, this is how I. Is there a big way to point?
You have a laser. That's on the right. Yes. On the right after the. Yes, this one. This one is the laser.
This is I think better. So right. So the size will just be the sum of the non-zero parts, and we'll depict this by its Young diagram, which will be. For me, it will be a left justified sort of inverted staircase where the sizes of the rows are going to be given by the parts of the partition. So, I think the example here should indicate the rule. So, for instance, because we start with 7, we have 7 boxes in the first row of this array, 4. You have 4 in the next, and so forth, going down. And we'll order partitions by containment of their shapes. So again, just I'll illustrate this with an example. Mu 421 is contained in lambda for the simple reason that we can see it sitting inside in the left corner of lambda. There's mu. And this partial order gives us, in fact, a lattice structure. And I can draw the Hasse diagram, at least part of the Hasse diagram for you. So up to rank 5, the partitions are arrayed in this following manner. Right? So this is what's called the Young lattice. And so this is it's ranked in the sense that it comes in levels, lattice, distributive lattice. And for us, or for me at least, what's important is that it's what's called one differential, which means that it's ranked. So it has these levels. So it's a ranked poset. It doesn't have to be a lattice, so you don't necessarily have to have the meet and join operations. But in addition to being a ranked poset, there should be two operators. So we have what's called a down operator and an upper operator. So the down operator just so these are operators on, say, complex valued functions on the lattice, and the down operator is just going to sum all of at lambda will just sum the values of psi for all mu which are covered by lambda. In other words, contained in lambda and differ in rank by 1. And dually we have an upper operator, and they together the one differential property is that they satisfy this Heisenberg commutator relation. So of course, in the Young case, this is not the end of the story. In fact, we have, if you like, higher up and down operators, where we are allowed to jump more than just one rank level at a time. We can jump 2 or 3, and in fact, there's an action of a full infinite dimensional Heisenberg algebra. But for our purposes, we only need this one finite dimensional Heisenberg algebra. And okay, in any poset, we can it will be important to look at what are saturated chains. So these are, if you like, paths in the Hasse diagram where you ascend one rank level at a time. So I've highlighted one here in red. And so if we have a partition, I'll declare its dimension to be just the tally, the total number of all such saturated chains, which begin at the empty partition and end at lambda. And this one differential property implies that this mapping that takes a partition to the ratio of this dimension, so the number of saturated chains divided by the factorial of its rank, that this is poset harmonic, meaning that it's normalized, so its value at the root of the poset is 1. It takes non-negative real values for all partitions, and phi agrees with the up operator applied to phi.
In this free, shouldn't, what do you mean here? Phi pi of lambda?
So so phi pi is this particular function given by this ratio. So these three properties are the harmonicity properties. In general, if I have any function phi from the Young lattice to the reals, say, which satisfies these three conditions.
Okay. Okay, sorry. This is the U you define at the
This is well, yeah. It's a little bit. The font is a little bit different. Okay. It's this U.
Okay, this U.
Right. Okay. So that's the lattice, and now the functions. So So just recall that so I would like to think of the algebra of symmetric functions as basically an infinite polynomial ring. So a polynomial ring in infinitely many variables, where these h's are the complete homogeneous symmetric functions. So these are going to be written as power series in some auxiliary variables x's. So we have some extra system of independent variables, x1, x2, x3, etc. And we'll just form all kinds of all possible monomials from these h's. Right? So given a partition with parts lambda 1 through lambda p, then we can form corresponding monomial h lambda. And these will form, as I vary over all partitions, this will give me a basis for this ring. And so with this basis, I can then I can tell you what the Schur function is. So the Schur function will be a particular combination of the homogeneous symmetric functions.
These are elementary symmetric or homogeneous? Is there strictly? Is I strictly lower than?
I is yeah. Sorry, that's a little bit hard to read. It's a weak inequality there.
Okay.
Yeah. It's a little bit hard to see, but it's a weak inequality.
It's small. Yeah, it's too small.
So the Schur functions will be particular combinations of these h's, and so the k here, k upper lambda mu, these are the, if you like, the inverse Koska numbers. So they're matrix entries of the inverse Koska matrix, right? Where k is the matrix. So this is a matrix whose rows and columns are indexed by partitions of a fixed size, and the Koska numbers, k lambda mu, lower lambda mu, these are, okay, I mean, in the language of Tableau, they're semi-standard Tableau of shape lambda and content mu. From the point of view of the Young lattice, if you like, these are chains, not necessarily saturated. So these are chains that are allowed to make jumps, and between, with the requirement that between, say, the k minus first partition and the kth, I have to add mu k boxes horizontally. So in other words, I'm allowed to do something like, can I write over here? Oh, good. I'm allowed to, if I have a box and I want to add 2 boxes, right? Horizontally means I can do something like this. I can, I can put a box here and here. But what's forbidden is I'm not allowed to do something like stack the 2 boxes beneath one another. Right? So this is forbidden. So in other words, I'm allowed to somehow ascend by without my blue boxes inhabiting the same column. So but glibly put, this number is counting certain kinds of chains in the Young lattice which terminate at lambda, and where the steps are somehow controlled by mu.
So could you have the partition 3, for example?
Yes, I could have so I could jump, if I added 2, I could go like that. That's perfectly good.
And the projection with semi-standard Tableau is just that in adding these 2 boxes, you label them with the same number, and this rule makes sure that it's semi-standard so that you strictly increase downwards.
Yeah, so that I'm weakly increasing, and the labelings would be weakly increasing in the rows, but always strict in the columns. But it's this post-set theoretic interpretation that I kind of want to replicate. That's why I write it. So, and then these Schur functions, they enjoy nice multiplicative structure. So if I take the simplest non-trivial Schur function, which is the Schur function corresponding to the partition 1, which I visualize as just a single box, right? And if I multiply it against any other Schur function, well, I can expand in terms of Schur functions lambda, where lambda is 1 bigger than mu, and it covers mu. So it's, if you like, it's all of the partitions in the Young lattice which share an edge with mu in the Hasse diagram.
Can I formulate this in terms of this up? It looks like the up kind of applies.
Yes, it is. It is the up. Yes, if you like, the up operator of S mu is. I would say the up operator of S mu is S. Yeah. It's like 10. Operator S mu is this in that language, kind of. And more generally, we can take products of arbitrary Schur functions. So if I take S lambda and S mu, where lambda is this means a partition of size m, and mu is a partition of size n, then the product will be expressed as also as Schur functions, but where the partition nu is a partition of the sum m plus n, and the expansion, the structure constants here, which govern the expansion, they're non-negative integers, also known as the Littlewood-Richardson coefficients. And I mean, there's a combinatorial rule for calculating these, which I'm going to not discuss for time's sake. But what is important here is that they have a meaning representation theoretically. So for given m, n, and the sum m plus n, we can form the corresponding symmetric groups. And it's a fact of the representation theory of the symmetric group that the representations of, say, Sm are indexed by partitions of m. And so for each of these symmetric groups, we can take some irreducible representation, so lambda, mu, and nu. And we can take the tensor product of the, say, lambda mu and lambda and v mu, and we can see that as a representation of the Cartesian product of the two symmetric groups. But then the Cartesian product of the two symmetric groups naturally embeds in the symmetric group of Sm plus n, where I just think of Sm as permuting the first m indices and Sn the last n indices. So it sits as a subgroup, and so what we can do is we can take this tensor product of the representations and induce it to the full group. And it will decompose in terms of irreducible. I mean, it itself will be some reducible representation. And so we can ask, what is the multiplicity of this v nu, and in its development? And it's precisely this same structure constant, this Littlewood-Richardson. So we'll see a kind of analog of this in the Young Fibonacci's.
You just Pierre rule is more general than you just in general. It would be a row.
Yeah, but okay, if you like, that's fine.
You don't need more.
Yeah, but if you like, it all is a special case of Littlewood. Okay, so yeah, before I go on to Young Fibonacci, so we'll want to upgrade these Schur functions. Let's now, instead of just dealing with one system of variables, we'll complement it with an auxiliary system, say of y's. Okay, and I mean, for the moment, we can think of these as two systems of independent variables, but eventually I'm going to want to specialize them. So keep in mind that these x's and these y's might be, typically will be taken to be, say, non-negative real values. And then also we'll want some kind of parameter gamma, which is between 0 and 1. And then what's called the supersymmetric Schur function. Right? So this is now a power series in two sets of variables. All right, and it's expressed as a sum over all mu contained in lambda times a product of two Schur functions. So here on the right-hand side, we just have a regular Schur function in the variables y, where mu prime means the so-called conjugate representation. That's the when I have a partition, right? I have this y equals minus x line, and what I can do is I can always rotate flip the diagram along this axis, and the result is the so-called conjugate partitions here. So I take the Schur function of the conjugate partition of mu in the y's, and then I take the so-called skew Schur function in the x's, where the skew Schur function is it itself is a sum of Schur functions, where the expansion parameters are exactly these Littlewood-Richardson coefficients.
I mean, if instead of mu prime you would have taken mu, then you would have recovered the S lambda of x and y. Well, I mean, not really relevant.
Yeah. I mean, this has the property, right? If I specialize, say, all the y's to be 0, then I'm getting back S lambda of x, right? And if I set all of the x's to be 0, then I'm getting the conjugate Schur function. I mean,
because it's super. No, I just if it was not super, I guess you would have replaced mu prime by mu, and you would have got ordinary Schur function. But maybe.
Yeah, I don't understand what you mean by. I mean, it would still be bivariate. Right?
But it's just x plus y. I mean, you add the variables. You take a Schur function with more variables.
Yeah. Okay. I mean, we can think of this, if you like. You can think of this as if you like thinking about the Schur function in terms of semi-standard tableau and is a generating function of semi-standard tableau. What you're doing is you're allowing to fill the diagram with two sets of indices, regular integers and some kind of complementary set of integers, and then you're but I mean, you really do want mu prime here. I don't believe. I mean, what I want to make are a bunch of functions which will still obey Littlewood-Richardson. We can come back to that maybe, but I think you really need this. So and then we'll want to sort of make this gamma deformation, which is this kind of binomial thing, right? Where I think it's more or less self-explanatory, but where dimension mu lambda here means I'm counting saturated chains that start at mu and go to lambda. This is kind of a curtailment of the earlier dimension function I introduced. And these deformed functions will, like, if the gamma is 0, we just get back the supersymmetric function, and if gamma is 1, we get power of the nth power of the Schur function for a box times this this Plancherel factor here. Right, remember, this is the this part, this dimension lambda over n factorial was the this example of a harmonic function, coset harmonic function.
If we set our y to be 0,
then you get something new. Even if gamma is non-trivial, you get.
So it's not all Littlewood or Whittaker or Jack or I don't know.
I don't think it's any of those. I think it's something in this, some kind of supersymmetric function, but it's not.
I've heard people talk about super Jack polynomials. Do you know if they are, which are also in two alphabets?
So I think with the Jack polynomials, what you're doing is you're taking, you're kind of changing your up and down operators. You're introducing weights on the edges of the Hasse diagram of the Young lattice, and so you're. I mean, these won't be Jack polynomials. It's a kind of different thing.
What is it called super?
Because of the well, okay, because I mean these should be if we look at a finite, if we curtail these, right, and we look at only finitely many x's and finitely many y's, then these should be the characters of a super GLN. So traces of the irreducible representations of these corresponding supergroup. But the reason I'm bringing them in here is because, so for one thing is that they still obey the Peary and Littlewood-Richardson rules. But moreover, in particular, I would say, if the parameters, if the x's, all of the x's and y's and the gamma altogether tally up to 1, then we can do the following trick. We can define a kind of reduced function, I call it S bar, right, which is this deformed supersymmetric function where I've divided out by this power of the box, and this reduced function will be poset harmonic. Right? Clearly, at the trivial partition, of course, it will be 1. By it will be, because these are always real, positive or non-negative, since all of the parameters are non-negative, these barred Schur functions will themselves be non-negative, and the Peary rule in this case, I mean, just reduces to this identity, which is exactly the harmonicity condition. Okay. So you get this. So for every collection of x's and y's and gamma which meet this condition, we get a harmonic function. And what's important is that any other harmonic function, lambda mapping to phi of lambda, can be written as some kind of integral over this kind of infinite dimensional simplex, right? It's all of these parameters which sum up to 1, where the measure that you're integrating with is some unique probability measure which is determined by phi. And in this case, we say that the simplex, right, is the Martin boundary of the Young lattice. So every other, if you like, the given an arbitrary harmonic function, I can kind of always solve the kind of Dirichlet problem with respect to this boundary that I've kind of added to the Young lattice. And now with the, okay, now going to the, so those are those are the aspects that I kind of see as being important in the Young case, and all of these I would like to somehow see their images of in the case of this Young Fibonacci. So with Young Fibonacci, what's happening is that at a combinatorial level, partitions are going to be replaced by some kind of binary words, which are called Fibonacci words. And the Young lattice will be replaced by some partial order that we can put on the set, the entire set of all such words. So what Fibonacci words are simple enough. They're words with digits. I think of them sort of growing from the right to the left. That's why I've indexed them this way, A1 through AK, where each A is either a 1 or a 2. And as a set, YF is just all Fibonacci words. But we're going to rank it, or sort of cut it into layers using a rank function. So the rank of such a Fibonacci word will just be the sum of its digits. And so if I declare YFN to be all of those Fibonacci words which have size or rank n, it's a moment's reflection leads you to understand that the size of this cardinality of this set is just the nth Fibonacci number. So hence the use of the adjective. And then we can put a partial order in this. Okay? So, and what I'll do is, instead of telling you what the partial order is in general, I'll tell you what the covering relations are, or if you like, I'll tell you what the edges of the Hasse diagram are. And from that, you can, by transitivity, get the definition for any pair. So given V and W Fibonacci words, we'll say that V is covered by W if W has its rank is 1 larger than V, as it should. And we can get W in one of two methods. We either take V and we prefix it by 1, or we take some U and prefix it by 2, where U is something that is previously covered by V. So from sort of 2 layers before W. And this is some kind of recursive procedure of building up the edges. So, using the previous level and possibly in this second case the layer before that. So here's a picture. Again, up to rank 5. So rank 5 is down here. So you start with the empty Fibonacci word, right? And then there's only one thing you can do to get the unique Fibonacci word of size 1, which is to prefix the empty word with 1. So we get 1. And now to go to rank 2, we can either take this Fibonacci word 1 and prefix it with 1 and get 1, 1. Or we can realize that the empty word is covered by 1 and prefix the empty word by 2. And thus we get 2. Let me just do one more. So like starting with, say, now 1, 1, we want to go to rank the next level. We can either prefix it with 1 and get 1, 1, 1. Or we can take the thing that it covers, which is 1, and prefix it by 2, and hence get 2, 1. And so this will go on. Yeah?
Is the second rule different from saying that if the word starts with 1, you replace the 1 by a 2?
Yeah, so you take, if you like, you read the word from left to right, and the first occurrence of a 1 may be replaced by a 2. The first, yeah. Yeah. And, yeah. So, and you can see, okay, level 3, level 4, level 5. At level 5, we have 8 Fibonacci words, as we should. And you'll notice that, maybe it's not obvious, but up to level 4, actually this poset structure is the same as the Young lattice. So up to, for the first 4 levels, these lattices agree. But starting At level 5, you get something new, for the simple fact that the 5th level of the Young lattice has only 7 elements. There are 7 partitions of size 5, whereas there are 8 Fibonacci words of size 5. So this is where the discrepancy begins. But nevertheless, this lattice structure, I mean, this poset structure makes this into a lattice. So it's ranked one differential lattice, just like before. And in fact, more is true. So the Young lattice and this YF, the Young Fibonacci lattice, so are the only one differential lattices in existence. There are many one differential posets, but if you restrict yourself to posets that have meets and joins, then you have basically 2 options. So this is why I guess there's sort of a focus of attention on YF, is because it's somehow really the only other option to the Young lattice in this world of this basic Heisenberg relation for the up and down operator.
Just outputs the sum of all the things that are directly above and down does the same for below. That's the definition of these up and down functions.
Up is you sum everything,
Covering.
rank 1 more, and down is rank 1 less, and then they should compute.
So I should see some of these as Young diagrams and some of them are not.
Yeah, I mean up to here, up to level 4, I could relabel these, but with.
And then the next one, can you see those which are Young diagrams and those which are not?
So there is a way of labeling them with Young diagrams, but they wouldn't be Young diagrams with 5 boxes. They would be this. I would
related to this matrix with 1 and 0.
Like these in the scale risers.
Forget this special matrices which are just where you have 1 and 0s, which are -1 also.
Oh, you mean alternating sign?
Yes.
Not that I know of. But it would be very nice to have some. It would be very nice if there was a coherent way to associate to any Fibonacci word partition. But I mean, I don't know if this. And part of the problem here is part of the problem from doing such a thing is that somehow the Young lattice enjoys something, or the Young lattice and the symmetric groups enjoy something which is called Schur-Weyl duality, and this is something that is somehow absent here, or at least it's not self-evident.
Do you just want to relabel them by partitions, or by partitions such that at each level the weight of the partition is the same?
Yeah, you would want certainly the ranks to be the same. You would, well, I mean, okay, you would want several things. Maybe let's. Maybe I could return to that later if we have time, because there is an interesting story with this 6th level. Okay, so again, just like in the Young case, we can consider the saturated chains, and as before, I'll define dimension of a Fibonacci word to be the total number of saturated chains ending at W. And again, because this is a one differential poset, this function, mapping U to the dimension of U over its rank factorial, this is poset harmonic. So this is the.
So before this dimension was actually the dimension of the spec module of associated to the partition lambda, right?
Yes.
And so here is there
Yes.
Can every Fibonacci word also be associated to some representation of something nice? I guess.
Yes.
Okay.
Next slide. Well, okay, we'll get to it. Okay, so now that's the combinatorics. If you like, what about the kind of what plays the role of symmetric functions here? So now, okay, we'll take two systems of independent variables, x's and y's, and we're going to be working inside this big polynomial ring, which involves both, all x's and y's. That's our universe. And okay, first we need to make a kind of analog of the clone homogeneous symmetric functions. So given a Fibonacci word, I define something called HW. Okay, starting with the empty word, which I just declare to be 1. And okay, in general, what I'm going to do is I look at the word, and whenever I see a 1 in the word, I'm going to replace it by an x. And if I see a 2, I replace it by a y. And that's what this recursion is sort of saying, except the index of the x and the index of the y is going to record sort of how its position measured from the right of where it occurs, right? So for instance, if w is, can be written as v with a prefix of 1, then the corresponding h will be, h of the v with an x, but the index is the rank of v plus 1, right? So the indices are increasing as you move off to the left. And the same with if you have a prefix of 2. So you get this supply of monomials. Okay, so each of these is a monomial. And I'll declare omega to be just the span of these guys. So this is some infinite dimensional subspace of my ambient polynomial ring. And here I'll define a so-called shifted product. So for these h's, so hu shifted with hv is, so I take hu and what I do is I shift all of the, whenever I see an xk occurring in this left factor, I substitute x of k plus r, where r is the rank of v. And whenever I see a y, I replace it by y plus y sub k plus v, the rank of v. So I advance all of the indices of the x's and y's depending upon the rank of the right-hand factor.
Isn't it just the product isn't it h of the concatenation of uv?
Yes, it is exactly that. Yeah. So this is h uv. And which is clearly non-commutative. Right? So we're living inside of this commutative algebra, but we're using a different product. And then we extend this product by linearity to the entire span, right? And so this omega then becomes an associative non-commutative algebra, right? And that object is called the clone symmetric function ring, even though there's nothing symmetric about it. And now, yes. Okay, now inside of this we can define analogs of the Schur functions. So again, they're going to be expanded in terms of the homogeneous functions with some structure constants, which are, there shouldn't be a tilde here. So these will be inverse clone Koska numbers, okay, where the clone Koska numbers k, u, v. Again, these are going to enumerate certain kinds of chains in the Young Fibonacci lattice. So chains that begin at the empty word and end at u, and where the jumps are somehow controlled by v, right? So in some sense, it's morally close to the usual Koska number. Except I don't have a tableau interpretation of this in any obvious way. That's why I prefer the chain description. So, So yeah, so if I parse V in terms of, if the A's are its digits, then the jump between the words UI minus 1 and UI will be related, will be a covering relation if the digit is 1, and if the digit of V, corresponding digit of V is 2, then UI will be obtained from UI minus 1 by putting a prefix of 2. So you're allowing a jump of more than 1 at that point. And alternatively, I can write these clone sure functions as kind of shifted products of determinants. So I let AK be this k by k tridiagonal determinant where I put the x's on the main diagonal and the y's on the super diagonal. And I also make an analogous B. It's the same thing. It's basically the same thing as A, except the top row is slightly different. And then I can recursively obtain this clone sure function. If V is just a string of ones, it's just AK, and otherwise I can write V as some prefix of ones, a 2, and then some suffix. And the corresponding SV will be whatever the clone sure function was for the suffix, which we get by induction, times this B factor, by shifted B factor.
B is supposed to be independent of x2, for instance. Or was that a typo? Is that a typo?
What?
So x2 and y, the x2 does not appear in B. Is that correct?
Oh, yeah, x2 doesn't appear, you're right. Yeah. Okay, and then we have analogous Purian-Littlewood-Richardson rules. So if we do the shifted product with the simplest non-trivial clone sure function for S1, that's of course the same as just multiplying, in the usual sense, by xn plus 1 against SV. And it expands these clone sure functions one step higher and which cover V. And again, we have a Littlewood-Richardson shifted product of SU and SV can be written as SW, where W has rank m plus n. And these structure constants are again non-negative integers. And here we get the representation for it. So for every n, or m, every rank in the Young Fibonacci lattice, there'll be a so-called, there'll be a semi-simple algebra called the Okada algebra. This will be our analog of the group ring and the symmetric. And the irreducible representations of this Fm will be indexed by the Fibonacci words of rank m. And so given these three, Fm, Fn, and Fm plus n, we can take 3 irreducible representations corresponding to Fibonacci words. We can take the tensor product of VU and with VV, right, and induce it in the same way. We have, of course, it turns out a natural inclusion of the Cartesian product of these algebras, the big algebra, and then we can do we can decompose this big representation, and again we recover these structure constants as multiplicities.
There's a combinatorial rule like the Littlewood-Richardson's one.
Yes. So in fact, their rule is very similar to this. It's very reminiscent of this rule for the clone Cosca numbers. It's slightly more complicated, but the same kind of thing. Maybe a quick word about these algebras. Okay, so these Okada algebras, Fn, these are unital associative algebras. They have like a kind of Coxeter-like presentation. So they have Fn has n-1 generators, and instead of being generated by involutions like the symmetric group, they're generated by kind of quasi-idempotence. EI squared is EI, but with this parameter xi showing up. So now we want to think of the x's and the y's really as some complex numbers that we've chosen. These generators will typically commute as long as the indices are far enough apart. And if they're neighboring, right, we get this triple relation, which involves the y parameter. And then, okay, it's the results of Okada. This algebra has, if you like, just in virtue of the one differential property of the Young Fibonacci lattice, this algebra has dimension n factorial. And it will be semi-simple precisely when the clone-Schur functions of rank n are all non-vanishing. So these clone-Schur functions tell you about, when you cease to be semi-simple.
For which n is this true?
For all n.
So it's always true.
Yeah.
It's always semi-simple.
Yeah.
And so this looks a bit like temporally leap, except that you kind of miss one of the relations,
Yes.
right? So this allows you to have lots of different x's and y's, which you couldn't for temporally.
Yes, right. Yeah. Yeah. In fact, indeed, there is a nice relation with temporal leap. I mean, so when these parameters, when all of the parameters all of the x's and y's are all equal to, say, delta, then you get a surjection into temporal leap. And in fact, there is I think, a kind of conjectural way, diagrammatic way of visualizing this algebra using the temporal leap diagrams, but then somehow decorating the arcs in some way. So there's a relation.
In that case, it arises as a quotient of Hecke. Do you have some sort of analog of Hecke here, or the Hecke algebra?
No. We have, okay. We don't. We have, it turns out, a kind of Qification of the Young Fibonacci lattice, in the sense that we can add parameters onto the edges and, and kind of introduce into these up and down operators and get a whole kind of Q version of this theory. But so far, I haven't seen it manifest as an algebra. I may have to cut it short here, but let me just end here with some. I mentioned we should talk about specialization. So I'm going to declare. So now x and y are sequences of complex numbers, right? And we'll say that the pair is Fibonacci positive if the corresponding evaluated, clone-Schur function is strictly positive for all Fibonacci words. So this is the same as saying that this infinite tridiagonal matrix made of all of the x's and y's must be totally positive, meaning that all of its non-vanishing minors must be positive. But more than just that, this BK infinity, right, which is the following tridiagonal matrix, right? This also has to be totally positive. And all right, and we'll just let P be the set of all pairs which are Fibonacci positive. And then, well, okay, we can introduce a kind of barred clone-Schur function where we divide off by, if U is of rank n, we just, if you like, we divide off by the first n x's, and this barred clone-Schur function, well, it will be poset harmonic, right? It will be 1 as the empty word. It will be strictly positive by the Fibonacci positivity requirement, and it will, and because I'm dividing off by the x's, it will meet this harmonicity condition. So, if you like, the set of pairs of Fibonacci positive sequences gives you this big supply of harmonic functions on the Young Fibonacci lattice. But it is not the Martin boundary, it turns out, of the Young Fibonacci lattice. So this was studied by Goodman and Kareff in 1997, and per their understanding, the Martin boundary of the Young lattice can be seen as pairs, gamma W, where gamma is some parameter between 0 and 1, and W is basically an infinite Fibonacci word, right, where with some kind of convergence property, right, where so this D of W is the sum of the positions of the twos, right? So every two has a position which is defined by this. So K is the kth occurrence of 2 in W, and this is how you define dk of W. And sorry, this should be inverse. It should be a -1 here. So, yeah, so the sum of the reciprocals of these dks should be convergent. So we have all pairs like this plus an extra point, which corresponds to this Plancherel measure, to this function that that sends a word to dimension of W divided by W. So that means that somehow, we should be able to write a Fibonacci positive, a sure function evaluated at the Fibonacci positive pair as some kind of integral over this Martin boundary. Although, to me, this is still a mystery of how to actually implement this. So, okay, I guess maybe we could end here, but a problem for me, which is interesting, is to somehow characterize or parameterize these Fibonacci positive pairs of sequences. They're very hard to find, but I do have some. And so, for example, one example is to just specialize all of the set xk and yk to be k for all k. In that case, you recover the Plancherel function. And then there are some deformations of this. You can introduce a deformed Plancherel evaluation, shifted, some kind of combination of these two, shift deformed, and then finally called the Ziegler evaluation, which is related. This is related to Q-Hermite functions. Right. But so far, these are this list is small, and it would be nice to sort of have a better understanding of what these positive evaluations are. So I think I probably should end there. I have more, but I think I don't want to.
You say there is a kind of way to represent it with this, like temporally lib. I guess you could put an arbitrary weight to the loop, but I don't understand. Probably it's more complicated than that.
Well, the idea would be something like this: you take a temporally lead diagram. I don't know, right? And then you imagine cutting it in half. Oh, let me change the cover.
Do you want a cup at the bottom or a cap? You want two caps at the bottom or?
Oh yes. Something like this. Right. And now imagine cutting this in half so that we get two half diagrams. Something like. And now what we can do is when we have these half diagrams, we can kind of we can make a kind of tree, right? We put a vertex on each arc, right? Plus a sort of root vertex. So actually, in this case, the root vertex would be sort of going like this. And then you can, the decoration would correspond to making a linear extension of these two trees, which are duals with half diagrams. So that could, there's only one linear extension for this chain, right? It has to be 0, 1, 2, 3. But for instance, here we could do 0, 1, 2, 3, etc. So what you would do is take two linear extensions of these half diagrams, which have to be compatible. I mean, they have, whatever the label is for the propagating, for the arc that joins the two sides, it would have to have the same label. And as long as that is consistent, then we can glue them back and we get a labeling of the entire temporal lead picture. And then somehow the multiplication, so then what you're dealing with are young temporal lead pictures plus this kind of linear extension. And the product somehow, there's a product which takes this data and produces, well, it's the same diagram that you would get by taking the product of the temporal lead diagrams, but somehow you get a new linear extension from the two. And this should be a model of how you multiply it.
Yeah, nice lattice models to be discovered.
Yes, yes. I mean, it would be nice to have going back to this algebra here. It would be very nice to have some kind of maybe spin chain interpretation of this, right? I mean,
the third one, you don't have the other one with EI plus 1 EI.
Right. So temporal lead would also involve this. So we have no relation on this. This is an independent element in this algebra. So, I mean, there are a lot of problems related to studying this algebra, like just understanding its central idempotency is a challenge. Understanding its Giuseppe-Murphy theory is another interesting problem. So, no, I am working on it. I mean, the trouble with the Giuseppe-Murphy theory of any tower of algebras is that it's fundamentally underdetermined. You have to ask you have to put some constraints on your Giuseppe-Murphy theory to kind of make life interesting.
I don't know, you think of your chain of Fn sitting inside Fn plus 1 and so on, and then you look for the centralizer of Fn inside Fn plus 1, and there should be, at least this is how for Sn, how I guess.
Yeah, I mean, so certainly I make this, I make a Gelfand-Sedlin algebra,
Right, exactly.
which is direct sum of the centers of these. And I'm asking for generators, but there are many choices for Giuseppe. Yes, the point I'm trying to make is there are many choices for Giuseppe-Murphy elements. You ideally you want to constrain things by imposing some kind of identity. Like in the case of the symmetric group, you have this identity that says 1 plus jk, the product, k equals 2 to n. That this is something like the sum over all permutations. Let's make this a t, not a 1 t. Will be 2 t to the number of cycles of sigma, right? So I mean, ideally, I mean, in order to constrain these generators, you want some kind of identity like that. Otherwise, you have many choices of generators. And in fact, there is some analog of this identity. I mean, it doesn't pin down it doesn't precisely pin down these JKs, but there is a supply, let's put it this way, there is a supply of juicy Murphy elements that obey a kind of relation like this for the Okada algebra. So this algebra is kind of holds a lot of interesting problems.
Yeah, well, it's a bit vague, but if you take the Young diagrams, you can view them as a basis of a Verma module of the Virasoro algebra, right? Then if you take the Fibonacci Young diagrams, it looks like you have a slightly different algebra, which is...
So when you say that, I mean, so are you talking about this, I mean, you have this full infinite dimensional Heisenberg algebra action on the ring of symmetric functions, which I think can be upgraded to a Virasoro algebra action. Is that what you're referring to?
Yeah. Or maybe just if you look at the diagram you had at the beginning, it looks like just the structure of the module of the Virasoro algebra.
So the whole thing,
the whole thing, yes. The infinite dimensional module.
Yes.
And now, if you go to the Fibonacci version, it looks like instead of using all the generators L-1, L-2, etc. of the Virasoro algebra, you're just using L-1 and L-2, but you forget that they have algebraic relation inside the Virasoro algebra. So it looks like a generalization of the Virasoro algebra, actually.
If that was the case, it would be very nice. I mean, it sounds like covertly this omega that I introduced, this clone function, right? I mean, covertly this is isomorphic to the free algebra in two variables. So if you like, non-commutative polynomials in two variables, and I mean.
Yes, so
perhaps
to me it looks like these two variables, you could interpret them as the two generators L-1 and L-2 of the Virasoro algebra. But you could, well, if you impose some extra relations between these variables, you could go back to the original Young situation. And if not, well, I guess you have a generalization of the Virasoro algebra and its representations. So, yeah, I wonder what this means.
I would be very keen on such an interpretation. I mean, I think I would like if you could say a bit more about it to me afterwards. But I mean, another problem here, which I would like. I mean, this is, as I said, this lattice is one differential, but it would be very nice to see if there was a full infinite dimensional Heisenberg action. So if we can introduce not just one-step creation and annihilation operators, but higher ones, right? So that we get, for every integer, we get a pair of such operators. And I've searched for it, but I can't find it. Because if you could, then you really could make a representation of the Virasoro algebra, the usual Virasoro algebra, which would be interesting. So far, that's eluded me, I guess.
I mean, Heisenberg is this relation U.
Right, but I mean, so for every k an integer, right, you want to have a uk and you want to have a dk with a commutation relation. Maybe with a parameter here in front, maybe with a scalar, right? I mean, so for in the one differential case, you just have one pair, right? But you would like to have infinitely many pairs, right? So U2 and D2 would correspond going up 2 steps and down 2 steps. Right? And for the Young lattice that exists, and that's integral in this boson fermion correspondence. At least the combinatorial manifestation of it.
Let's thank Jeanne again.